Hi, in this video I'm going to be going over how to code two fan carts that are moving across a level surface. One fan cart has twice the mass. This cart that's closer to us than comparatively to the other fan cart. And we want to be able to visualize this, simulate it using coding, and also see it graphically in the coding world too. All right, I've opened up Glowscript and I'm going to create a program. Okay, so I've got Glowscript open up here. I'm going to just copy these lines down here. That's just setting the background of my screen white and a certain width and height. Next, I'm going to add the ground. It's going to be 50 units horizontally with a thickness of 1, and it's going to go back in the screen by 5 units. And then I'll add my two carts. I'm going to make them as boxes. One's located to the left at negative 20 units, and the other one's also to the left at negative 20, but you'll see that in the Z direction, one's a bit back at negative 2, and then one's a little bit forward at 2. All right, we have a blue one and a purple one. M refers to the mass. I'm just going to add that as an attribute, and 0.5 is the other mass. So one is twice the mass of the other, as indicated in the problem over here. I have a 500 gram, and the other one is going to be double that mass, which is going to be 1 kilogram. Okay, and then this is just going to simply leave points behind, and then at an interval of every 30 times. Okay, let's take a look at what that looks like when I run it. Okay, and when I run it, I should see 2 blocks, but maybe I want to kind of shift it so I can see it more like this. So I'm going to add a little line in here where I'm going to change the center of it a little bit off center, so that way when I run the program at the beginning, it is going to look a little bit off center, as you can see here. Okay. All right, the next thing I need to do is define a few other properties. We have the fact that the carts are going to be starting from rest, and there's going to be a constant flow of air going out backwards, so that will be a forward force. Now we're choosing a force of 0.2 newtons in the positive x direction. And we're going to run it for 10 seconds, that force, and then eventually just going to coast along. So back into our program over here, we need to add in a force vector, which I'll put in here. It has 0.2 newtons in the x direction. We also have the velocity, which will be 0 initially. And we're going to make the increment of time, I don't know, we'll go 1 over 50. Okay, so 1/50th of a second is our little time steps. So we've defined the masses of the carts. We've defined the force, that's the same for both of them. We've defined their initial velocity. And we have the time step. One thing we haven't defined yet is the cart momentum. So I'll write cart A dot P, which is my symbol for momentum, rho. And remember, momentum is mass times velocity. So I'm going to take cart A's mass and multiply that by V. And then I'll do the same thing for B, and that will be cart B dot M times V. And now I've defined the initial momentum. Now the initial momentum is initially 0, but I need to define that variable before I start getting into a loop. Okay, I think we're ready to start doing our loop where we're going to make these two objects move. So we're going to use a while loop, okay, and we'll have cart A dot pause dot X. We'll continue moving that until it gets to the very right side of the ground. Now the ground is 50 units. It's centered at 0, right, along the x-axis. So the right edge would be at 25. But also remember that the carts have a width of 2. And so when we're talking about the position, it's in the center of it. So really, we're going to continue the loop until it gets to really 25 minus 1. So that's the width of it. So that's 24. And cart B, it doesn't matter, I guess, which one is going to go faster, okay, is also less than 24. So that's our condition that we're going to keep running that loop until, as long as we're under that condition where it's less than that. We're going to slow our animation. That's going to be 1 over our increment of time. That's the rate. And now comes the part where we update. Now we're going to use the Euler method of updating things. Okay, so what are we going to do in that loop? Let me kind of try to explain this maybe a little bit on a written form. So in that loop, the first thing we want to do is we're going to calculate the change in momentum, which is called the impulse, and use that to calculate the new momentum. So the new momentum will be equal to the old momentum plus that change in momentum. Now, how do we find that change in momentum? If you recall, back in our chapter 7 notes, remember that momentum is equal to force times time. All right, we can calculate the new momentum by using, or calculate that impulse by taking the force and multiplying by the time interval. Okay, if you recall, you had a force versus time graph, and let's just for simplicity assume that the force is constant, which it is in this case. And if you take a little increment of that time, I'll call that delta t, and you multiply by the force, you end up with the area of that little rectangle. And that area represents the change in momentum. So we can find the new momentum by taking the old momentum we had in the earlier step and adding this change. So the new momentum, all right, will be equal to the old momentum plus F times delta t. And delta t is going to be what we call dt. So back in our coding world, that would be simply saying that, oh, where am I here? There we are. Cart A dot P for momentum is cart A dot P plus F times that little chunk of time dt. And then we're going to similarly do this, by the way, for cart B. So we're doing two carts, remember. Okay, so there we go. So what's the next step that we do once we have calculated the new momentum? So the next step is to find the final velocity, and we can find the final velocity or the new velocity by the fact that momentum is mass times velocity. So if you just take the momentum that you just got and divide it by the mass, you'll get the cart's velocity at the new step. So let's put that into the coding perspective here. Let's see over here. And so we're going to add in a line here. I suppose you could say that cart A dot V is cart A dot momentum divided by cart A dot mass. And then we can do the same thing with cart B. Okay, so we now have the new velocity. Okay, so what's the next step? Okay, so now we need to update the position, and so the position, the new position, will be the old position plus that change in position that it experienced. And if you recall, if you take, say, a velocity versus time graph, let's say it's going something like that, if you take a little chunk of that area, right, dt by v, you'll get that area represents that displacement. So if you take the velocity that it just had and multiply it by that chunk of time, then you get that displacement, and so you now updated the new position. So let's put that into the coding perspective here. Okay, and so we'll now need to update the position of both the carts. So cart A dot pause. So let's do it in all three dimensions. Will be cart A dot pause plus cart A dot V times dt. And so then we're going to do the same thing for the other cart. It's going to be a little bit different because they have different masses, right? Okay, so we're hopefully getting there now. And so I think we're ready to start it. Now, we may want to keep track of the time, so we can say t equals t plus dt. And if we run it, let's see if I have made any mistakes. Oh, I have. Hello. Okay, I was running it, and I noticed I had an error. I'll just show it to you here. I have t equals t plus dt. And let me show you that. It looks like I had forgotten to define time. I was looking for t, I didn't know what it was, and you can't obviously introduce it in the loop. You need to define that variable. The second thing is, after I ran it here, I noticed a couple other things that happened. It looked like the carts were on top of each other and they were moving together, and I was trying, what's going on here? And I made some silly typo errors. I see that I was looking carefully in here and I saw that cart A is defined properly, but cart B, I'm defining it based back to A. So it moves it and pretends it's right in the same position of A. So this should have been all B in here. I think in here, this is hopefully correct. I had cart B, this mass divided by that. I think this was originally MA. So now if I run it, hopefully, it's going to be running properly here. So I have two blocks that are now moving, and yeah, you can see the purple block that is half the mass of the blue block is accelerating at a larger rate. Now, it's continuously accelerating until one of them gets to the very edge of the thing, and then it's done. But let's suppose that I wanted to run it for just, say, 10 seconds, because that's, after all, what we're doing. So it's going to only be on for 10 seconds, the fan, and then it's going to coast afterwards. So how do we do that? So the way I'm thinking is to put an if statement in there. So if we maybe put a little if statement in here, like if, for example, like we're keeping track of time, right? So if t is less than 10 seconds, then what we should be doing is updating the momentum and updating the position and so forth. So let's say we make that as part of our if statement. All right, you can keep calculating the velocity outside of it. Doesn't really matter. This could be in the if statement. I suppose we could put that in there, right? But we do want to keep updating the position. So once the fan turns off, then the object is just going to continue moving at constant velocity. Regardless whether this is in the if part or not, still work. So hopefully now if I'm running it, all right, let me just run this program here. You should see that now they are going to accelerate for a time of 10 seconds, and then after it reaches 10 seconds, it's going to stop accelerating, and you should see them coasting. So maybe right about now, I suppose. Yeah, you can see them now. The dots are equally spaced in here. Okay, so another thing that we could look at is doing the graphical piece. Okay, so first I'm going to just kind of copy some code in here. And this is where I define the graph. Okay, so graph 1 is have a width of 800, height of 200, and the title, time, and velocity, and it's going to go from 0 to 15. That's the time scale, so we're going to go to like 5 seconds. And then y minimum is going to be 0 to 5. That's basically it. Okay. Next, we're going to plot two different functions in the graph. Okay, one for cart A and cart B. All right. So we're going to be plotting, depends what you want to plot, momentum or velocity over time. Okay. And then within the loop, we need to actually then tell it to keep continuously plotting it. Okay. Oops. So now I'm going to add in these lines in here. This is going to be plotting on the x-axis time, and then plotting here. Well, it depends what you want to do. You don't have to. I actually initially hadn't calculated the velocity earlier in my other program. So actually, since I'm calculating the velocity, I can just say calculate, put the velocity on the y-axis for both of them. So now when I run it, hopefully, we should see a graph being plotted at time. Ooh. What does it not like here? Cannot plot a vector. Oh, good point. Yeah, so I am plotting a vector. I can only plot a scalar amount. So really I have to put in just the x component of that velocity is what we're going to be plotting. Can't plot a vector in a two-dimensional graph here, right? So let's try that, see if that works out. So we'll just be basically plotting the velocity of the two carts over time. Okay, and so you should see it nice and linearly increasing. You can see that the purple one is accelerating at a greater rate. Why? Because it has half the mass. All right, and then once these carts reach 10 seconds, then it's just going to continuously move at a constant velocity. Okay, so hopefully that makes sense. If you have any questions, feel free to ask me in class.